All right. Hello, welcome to our Fluids and Waves lecture tonight. This is the second week of our 15-week question-based lecture program. I'm going to wait a couple more minutes to see if anyone shows up, but if not, I will get going in a few minutes here. All right, I'll get started here. Hello, everyone. So my name's Anthony. I am going to be giving a lecture tonight on fluids and waves, waves dealing with sound and light. I'll be going over 8 MCAT style questions and then going over relevant content material after I review those questions. And depending on the questions, I'll give 1 or 2 minutes to answer those questions, and then we'll see the responses afterwards. All right. So this is the consent to audio or video recording release. This basically just is saying that by entering this meeting today, you are consenting that we can share this on our platforms. And in order to maintain your confidentiality, we encourage you to change your name and also to change your profile picture during this lecture. Here I have linked our GroupMe. This is where you can ask questions, and you can also answer other people's questions, and we'll try to, as tutors, get your questions answered. I have our Instagram handle here, so this is where you can see our relevant updates, and on our YouTube channel is where we have all of our content. So this is, we will have 2 lectures a week. On Sunday, we'll have a recorded release, and that will be uploaded to our YouTube channel at 8:30 p.m. Eastern time. And then on Monday, we will give a live lecture from 8:30 p.m. to around 9:30 or 10. All right. So here we have our first question, and this is based on fluids and pressure. So first, I want to just make sure that we are answering these questions as you would an MCAT style question. So depending on the question, you'll have I'll give everyone between 1 and 2 minutes to answer the question, but make sure you are carefully reading the question and thinking of an answer before you are looking at the answer choices in order to not get distracted by the answers. All right, so here is the first question. You can read it to yourself, and I will give everyone a minute or 2 to answer this question. All right, so I'll now go over the answer to this question. So the question says that a diver in a freshwater lake is 30 meters below the surface. What is the absolute pressure at this depth, and what is the gauge pressure at this depth? The density of water is 1,000 kilograms per meters cubed. All right. So after realizing which equations that I had to use and doing each calculation, I got that the answer was B. And then here on the next slide, I have the work shown. So this first equation here that you see at the top is the equation for absolute pressure. So its absolute pressure is equal to P sub 0, and that is the pressure at the surface of the liquid. And this is added to our density of the fluid and times the acceleration due to gravity. And then Z is your depth. So in this case, it would be 30 meters at which the depth that the diver is. So I plugged in my values here. For P sub 0, it is atmospheric pressure. It is important to realize that atmospheric pressure won't always be P sub 0. Let's say we are at an elevation that is pretty high. Let's say on a mountain, our pressure might be lower, but in most cases on the MCAT, our P sub 0 answer will be our atmospheric pressure. So I had my atmospheric pressure, and then I added it to the values that I was able to plug into this side of the equation here. And then I got my answer was 4.013 times 10 to the 5th pascals. And then for P gauge, it's essentially our absolute pressure minus our atmospheric pressure. So what the gauge pressure is telling us, it's that it's the same thing as absolute pressure essentially, but it is standardizing the value to atmospheric pressure. So it's just always going to be subtracted by our atmospheric pressure. So here we have 4.013 times 10 to the 5th pascals minus 1.013 times 10 to the 5th pascals. And we get that our gauge pressure is 3 times 10 to the 5th pascals. I will expand on these equations and specific things about them in the following slides here. But first, I will describe what a fluid is. So a fluid is different in a solid in that it flows and it takes the shape of a container. If you think of liquid water, for example, compared to an ice cube, when you have water in a glass, it's going to fill and take up the shape of the glass. But if you just put an ice cube in the glass, it's going to stay the same size and not necessarily take up the glass. Now, fluids can be liquids and gases. The difference between liquids and gases is that a liquid is incompressible while a gas is compressible. So if you are squeezing a balloon, for example, that has a gas in it, you can squeeze it and then decrease the volume of the balloon while also increasing the density of the gas inside the balloon, meaning it's compressible. But for a liquid, you can squeeze the balloon, but it's really just going to move the water around. And if you squeeze it past a certain point, it's just going to explode because it cannot change its density at all. All right, so describing a little bit about density and pressure. So for density, what density is, it's denoted with a rho, as you see here, and it's going to be our mass over volume. So for water, so an important value to know is the density of water, which is 1 gram per milliliter or 1 kilogram per liter, 1 gram per centimeter cubed, or 1,000 kilograms per meter cubed. So these are values that you can all get by interchanging the kilograms versus grams, milliliters versus liters, but it is good to know each of these values. So pressure is our force over area. The units for that is newtons per meter squared, as force is measured in newtons and area is meters squared. Atmospheric pressure is also important to know. In terms of pascals, it is 1.013 times 10 to the 5th pascals, as we talked about in our last problem. In terms of ATMs, it's 1, and millimeters of mercury and torr is both 760. And also an important point for pressure in water, for every 10 meters, our depth increases, we're going to increase our pressure by 1 atm. So our absolute pressure and our gauge pressure, we talked about these in terms of our questions, but what total pressure actually is, what absolute pressure is, it's the total pressure exerted by an object that is submerged in a fluid, while our gauge pressure is essentially that, just standardized to our atmospheric pressure. All right, so hydrostatics is our next question. Here's the question here. I'll give everyone a minute to think over the answer, and then we will discuss. All right, so I'll go over the answer to this question here. So this question says that ball 1 has a greater volume than ball 2, but both balls have equal masses, which will produce the greatest buoyant force when placed in a fluid. So when approaching this question on the MCAT, I would make sure not to read my answer choices first, as this could cause me to doubt myself and get distracted by the choices. The fact that C is the buoyant forces will be equal, and D is that I need more information, can just cause me to think differently that it is actually not ball 1 or ball 2. But first, if I did not look at the answer choices, I would try to think, what is the relationship between my volume and buoyant force? And this way I would then realize I should think about the equation for buoyant force. And that is, buoyant force is equal to the density of my fluid times the acceleration due to gravity, and times the volume of the fluid displaced. And because of that, we know our answer has to be ball 1. So our buoyant force is going to be the density of whatever fluid this is in. For both balls 1 and ball 2, it's going to be the same, as well as our acceleration due to gravity is going to be the same. The only difference here would be of the volume of our fluid displaced. Because ball 1 has a greater volume than ball 2, it's going to therefore displace a greater volume of fluid, therefore exert the greatest buoyant force. All right, so Archimedes' principle is essentially what is going to relate the volume of our fluid displaced and the volume of our object that is submerged in the liquid. So what our buoyant force specifically is, it's the force exerted by a fluid that opposes the weight of an object. So in last week's lecture, we talked about the normal force, which is essentially the same thing on the ground, where buoyant force here is what opposes gravity in a liquid. So it acts the opposite way that gravity does. It's also important to note that the buoyant force for a specific object is going to be constant, whether it is floating in a certain fluid or if it's sinking in another fluid. And then Archimedes' principle itself states that the volume of an object that is submerged in a fluid is equal to the volume of the fluid displaced by the object. Therefore, the buoyant force will equal the weight of the fluid that displaces it. And this can be seen in the equation we have below for buoyant force. And in terms of whether an object will float or if it'll sink, an object that is more dense than the fluid is going to sink. If it's less dense, it's going to float. And then when it's equal, it's going to be submerged in the water, but it's not going to be accelerating, meaning it's just going to be static and then sitting submerged in the water. All right, now Pascal's principle. So Pascal's principle basically states that when there's a change in pressure on one side of any type of container, that the pressure is going to be exerted at all points in the container equally. So if we're looking at this diagram here, we have our force 1 is pressing down on this side of the piston, exerting a force of P1. And so P1 is going to be exerted on every side of this container equally, meaning that P1 is going to equal to P2 here. Because we know that pressure is equal to force over area, we can then relate F1 over A1 is equal to F2 over A2. And this is how we can create a mechanical advantage and exert a greater force by just having a greater area over here. And we can create a hydraulic lift, and we see these problems on the MCAT. All right, so our next question here is going to be no longer about static fluids, but dynamic fluids. All right, so I will give everyone about a minute to answer this question. All right. So this question states, if the ratio of A1 to A2 is halved, then the ratio of V1 to V2 will. So I would try to think about what the relationship of our area to our velocity in a tube. So I know what the relationship is based on the continuity equation. So our continuity equation is A1V1 is equal to A2V2. In order to keep this constant, then in order to keep our flow rate constant, which our flow rate is equal to our area times our velocity, then our velocity here in this case is going to have to increase by a factor of 2 if our area is decreasing by 2. All right, so more about the continuity equation itself. So what the continuity equation measures is the flow rate of a fluid that is in motion. And this tells us that fluids flow faster through narrow passages versus passages that are less narrow. And I also want to relate this fluids in motion a little bit to medicine and our body, as sometimes it's kind of difficult to see how fluids can relate to or how physics can relate to medicine. But in terms of blood flow, this does relate. Although our blood flow in our circulatory system is not constant or laminar, meaning that it's not always having a constant velocity or it's not smooth, we can assume this to be true on the MCAT in order to solve for problems. So one important thing to note about our cardiovascular system is our arteries and veins. So as you can see here, we have our area and our velocity in terms of blood flowing through certain vessels. So we have our veins, venules, and then capillaries. Over here, we have our arterioles, we have our arteries, arterioles, capillaries, venules, and then veins. And in terms of blood flow, when our area of our vessels are the largest, meaning in our capillaries, so this might seem a little bit counterintuitive, but just because our arteries are bigger than our capillaries doesn't mean that our arteries have less area. We actually have more capillaries, and overall, the diameter of all our capillaries combined are bigger than our arteries. So you can see that here in terms of our area being really high, and then our velocity being really low, opposite for our arteries and veins here, which is essentially inverse. All right, so our question 4 is going to be another fluid dynamics question. All right, and I'll give everybody a minute or two to answer this problem as well. All right, so I will go over this problem now. So this problem states that for a fluid flowing through the tube above, so flowing over here to the right, does the dynamic pressure or absolute pressure at point 2 increase? So when evaluating this question, I'm going to want to think about the relationship of our dynamic pressure and absolute pressure and what that is. I know that Bernoulli's equation is what relates my dynamic pressure with my absolute pressure. So when looking at this equation here, I have P1, which is my absolute pressure, 1/2 rho V1 squared. That is going to be my dynamic pressure. So it kind of looks like the kinetic energy formula, which is 1/2 mv squared. So that is a good way to remember that that is related to that. And then our rho GH is basically our pressure based on our position. So together with that and P1, that is going to be our absolute pressure. And then it's equal to the pressure, or it's equal to this side of the equation, which is just the same thing at point 2. So therefore, if our linear speed increases at point 2, which it will because of the continuity equation that we just talked about previously. So at the same point here, so h is going to be the same in the side of the equation because you can see at both points that they're at the same spot. And then our linear speed is going to increase because the tube diameter gets smaller. Or it's going to increase so because our area of the tube gets smaller. Therefore, our dynamic pressure will increase because our velocity here is increasing. That means that we also know that our absolute pressure will be decreasing by the same amount. So now specifically about the Bernoulli's equation, and then the Venturi effect, which is just an application of Bernoulli's equation. So Bernoulli's equation is the sum of the static pressure and the dynamic pressure. And then this is for any incompressible fluid that is in motion. And as we talked about, this is the equation for Bernoulli's equation here. And essentially what Bernoulli's equation is telling us is that the more energy that's dedicated for a fluid in motion, the less energy that's going to be dedicated to the static pressure of the fluid. All right, so Now I'll talk about a little bit more about the Venturi effect and the Venturi flow meter, which is the application of Bernoulli's equation. So this is the same diagram that we used in our previous question, but I'll explain it a little bit more. So we know that at point 1 and point 2, we are at the same height here. So that side of our equation for the height for each side will be equal. But because we know that velocity is changing, then that is going to increase our dynamic pressure, but is going to decrease our static pressure and our absolute pressure. And this is seen here in the heights of the fluid in the tube. So this height here is different than the one that we see in our equation, but because pressure is going to be smaller, because the absolute pressure is going to be smaller, then less water is being, or less fluid is being pushed up into this pipe over here. So that's how we see less absolute pressure in this side, this part of the tube. All right, so now we will switch over to waves. We were talking about fluids, now we're going to be talking about waves, mostly in terms of sound, but also in light. All right, so our first question here, I'll give everyone a couple minutes to answer this question, and then we will discuss. All right, so I will now go over this problem. So the problem states if a wave travels 50 centimeters at 5 meters per second, what is the period of the wave? So first we have to think about what our equation is that relates our velocity. It relates our wavelength and period. So we know the equation that relates a velocity, frequency, and wavelength. And we also know that period is the inverse of wavelength. Using that information, I am able to do the work here that manipulates the equation for velocity of a wave. And in order to solve for the period, which will be period over is equal to wavelength over velocity. And at this point, I just plug in my values, but I am making sure that I am converting 50 centimeters to 0.5 meters and then 5 meters, and then using 5 meters per second in order to be able to cancel out the meters. And then I get 0.1 seconds. Yeah, it's important to make sure that you are also solving for seconds, as period is measured in seconds, while frequency is measured in seconds to the -1 power or hertz. So initially when I looked at this problem, I could have immediately crossed out A and B as they were not measured in seconds. And at that point, it's something that I need to just be able to move my decimal place over correctly. So I'll talk a little bit more about the description of waves, but first I'll talk about the types of waves. So first we have longitudinal waves. which are sinusoidal waves in which the particles oscillate parallel to the direction of propagation of the wave. So when looking at this diagram over here to the right, we see how our sound is going to propagate over here to the right, but our particles are also oscillating in this direction. So what is happening when you hear something is that the music system in this case is going to produce waves that are going to cause the air particles to bump into each other. And this will create expansion and compression, which will create wavelengths. And the air particles will bump into each other until it reaches your ear, then that's what you hear. For transverse waves, these are waves in which the particles oscillate perpendicular to the direction of propagation. So this is like light waves, for example. So we have the light is moving to the right, but our particles are oscillating up and down, creating this amplitude that's up and down. And then that our wavelength here, which is crest to crest or trough to trough, as it's shown here. All right, yeah, then just little descriptions of waves here. So what our wavelength is, it's our length from crest to crest or trough to trough of a wave. So here we have our wavelength measured here from this crest to this crest. You can also measure it here from this trough to this trough. The crest is going to be the top point, the trough, the bottom point of the wave. Frequency is the number of wavelengths that are passing through a certain point per time. While our period is going to be the amount of time that it takes to complete one cycle. So that's measured in seconds, again, the inverse of frequency. Where our amplitude here is going to be the magnitude of displacement in a wave. And again, as we discussed, our propagation speed is velocity equals frequency times our wavelength, and that's measured in meters per second. So for sound in particular, our frequency and our wavelength is associated with our pitch. Humans can hear between 20 hertz and 20,000 hertz, and then our amplitude is related to the loudness of the sound. All right, so now a question specifically about sound. So I will give everyone a few minutes to solve this problem, and then we will discuss. All right, I will go over this problem. So this problem states that a detector measures the intensity of a horn emitting a sound to be 10 to the negative 2 watts per meter squared. And then what is the sound level of the horn? So first I want to think about the equation that represents my sound level related to my intensity. So that equation is my sound level here is equal to 10 log times my intensity of the object that I have emitting a sound, and then I sub 0, which is going to be the intensity of the lowest intensity that the average human ear can hear. So basically here, I'm just plugging in my values for that I sub 0 value that I know, and that is important to memorize. My intensity, which is given in this problem, which is 10 to the negative 2. And then I'm dividing that, so subtracting the exponents, and then getting 10 to the 10th power. In order to solve that, I move my 10 over here, multiply those together, and I know log of 10 is 1. Therefore, I get 100 decibels. And sound level is also measured in decibels. All right, so now some equations and specific things about sound, like the speed of sound, sound level, and intensity. So the speed of sound through a certain solid, liquid, or gas can be represented by velocity is equal to the square root of the bulk modulus over the density of the object. So the bulk modulus is basically the elasticity constant. So how much it can be compressed or manipulated, while the density is just the density of the object that the sound is going through. It is also important to know the velocity of sound in air, which is 343 meters per second. And we also know that sound moves faster through solids than it does through liquids, and then it moves faster through liquids than it does through gases. So now, as we briefly talked about too, our sound level is equal to 10 log times intensity over I sub 0. This is measured in decibels, and essentially what we're trying to do with our I sub 0 value is, instead of standardizing it to a 0 value, we're standardizing it to a value that we know is the lowest intensity that human ears can hear. So it just makes more sense. And then when thinking about the actual relationship between intensity and sound level, we know that for every increase in intensity by a factor of 10, so if we're going from 10 to the first power to 10 to the second power, we will have an increase in the sound level by 10 decibels. And now for the intensity of sound. So intensity is equal to our power over our area, and that is measured in watts per meters squared. And then we also know that our intensity is proportional to our amplitude squared, and it's also proportional to the inverse of our distance away from the object emitting sound squared. So basically what that means is that as we are moving away from a sound, or the sound is moving away from us, the intensity is going to decrease exponentially. All right, and now I will talk about the principle of superposition, so wave interference. So here on this diagram, we have these waves that are interfering perfectly in phase, which means that the crests and the troughs line up exactly. And then graphically, we represent this as lining up between 0 degrees or also 360 degrees. When these waves interact, they're going to completely constructively interfere, and their amplitudes are going to double. Whereas for destructive interference, it's going to be the opposite, where my trough is lining up with my crest, and then opposite. And these waves will completely destructively interfere, and then you can see they no longer have an amplitude. In most cases, though, you'll get partial interference. So basically, the crests or the troughs won't perfectly line up, and you'll get some sort of a wave that ends up being between these two waves. All right, question 7. So this is about the Doppler effect. All right, I'll give everyone about a minute to solve this problem, and then we will discuss. All right, so I'll go over this question now. So this question states that a police car with its sirens on is traveling west and towards a student. If the student who is standing still wants to determine the frequency of the siren that she perceives, what information does she need? So we can determine what information she needs by the Doppler effect equation. So we get that the answer here is C. I'll go over the equation specifically, which is that the frequency that is detected is equal to the frequency of the source, and this is multiplied by the velocity plus or minus depending on which way the observer is moving, and that is going to be the velocity of the detector. That is going to be divided by again, the velocity minus or plus, that is the convention used here that I'll talk about in a second, minus or plus the velocity of the source. So in this problem, we know that our velocity of our detector, which is the student, is going to be 0. So we have this information right here, and that's because she is standing still, so she is not moving. The other information here that we need to find this value are frequency of the detector. So we need to know our actual emitted frequency. So that is our f sub 0 value. We need to know the speed of the sound, and then also the speed of the police car. So the speed of the sound, which is going to be this v value here, and then the speed of the police car, which is going to be our v sub s value here. And then looking at this equation farther, so it's important to memorize the conventions, the sign conventions used in this, and not to get confused of which one to use, because it is important and it will change your overall calculation. So the way I think of it is towards the top, in order to remember which one goes with which. So on the top here, we have that our observer moves toward the source, and that's when we use the plus value towards the top. So there's observer moving towards, so we use the v plus v sub 0. And then we use this top value as well if the source is moving toward the observer. So it's going to be v minus v sub s. Okay, so I also wanted to, again, relate medicine and the body to our discussion of waves here. So one of that is the Doppler effect and the Doppler ultrasound. So essentially, we just talked about the Doppler effect and the equation, but what that is telling us is that it's the change in perceived pitch that's associated with the source or the observer moving. So just the change in pitch, change of frequency, depending on the movement of the source. So ultrasounds themselves, they create images by comparing different densities of tissues. So they're going to emit an ultrasound, and the transducer is going to receive ultrasound reflections back that are going to reflect off of different densities of tissue, and that's how we'll be able to use that information, the speed, the direction of these reflections, in order to create images. Whereas for a Doppler ultrasound, we can measure blood flow rate, and that is because it uses the perceived frequency of the different reflections in order to determine the speed. So it uses that equation to figure out the speed of blood flowing through veins. This is an important thing because it can discover some conditions of the heart, some blood clots, things like that. All right, so lastly here is our last question. So we're going to be talking about electromagnetic waves, like light, for example. All right, so the first question here, I'll give about a minute, and then we will discuss and go over the answer. All right, so this question's a Roman numeral question. It says, which of the following, correctly demonstrates increasing energy in the electromagnetic spectrum? So first off, I want to start off by evaluating my answer choice that has two of the Roman numerals in it. So here I can go and I can evaluate A and C here as one shows up twice. So I have gamma rays, X-rays, ultraviolet rays. So I know that, my answer here is not 1 because that's wrong. We know that, as we see here on the side, that our lowest energy is going to, that our highest energy is going to be gamma rays. So this way is actually opposite. So we can immediately cross off 1. So cross off A and cross off C. We know that 2 is right and can evaluate 3. So we have microwaves, infrared rays, and visible light. And that goes along our spectrum here, going this way. So going from a lower energy to a higher energy. So the electromagnetic spectrum, important things to know about it is knowing which ways that is going from a lower energy to a higher energy. So a good way to remember that is the little saying that I have here at the bottom is that raging Martians invade Venus using X-ray guns. So these correspond to radio waves, microwaves, infrared rays, visible light, UV rays, X-rays, and gamma rays. So that is just an easy way to remember that. And the other thing that you want to remember is the wavelength of the visible light spectrum. So you want to remember between 400 nanometers and about 700 nanometers, with 400 nanometers being violet light and 750 nanometers being red light. So our red light here is going to have our lower energy, lower frequency, but longer wavelength, while our violet light will be the opposite. And then now just ending on some basic electromagnetic information. So what light and electromagnetic waves are is just that electromagnetic fields are changed by a changing magnetic field causing a electric field, and then could be also seen in the different directions. So an electric field creating a magnetic field. And the interesting thing about them is that even though they both oscillate perpendicular to the direction of propagation, they're also oscillating perpendicularly to each other. So they're oscillating on a X, Y, and Z axis, as you can see here. And then our velocity is going to be the same way we calculate it for sound. So velocity of light and velocity for sound, same for all waves. So velocity is going to be equal to frequency times wavelength. And then we know that the speed of light in a vacuum is going to be c. That value is 3 times 10 to the 8th meters per second. And that is also an important value to memorize. All right, and that is it. Thanks to everyone who came to the lecture, and everyone watching can email me if you have any questions about specific things that were talked about tonight. This is my email here. And then also feel free to reach out in the GroupMe with any questions or concerns, and we can discuss that there. All right. Thanks, everyone. See you next week.